Welcome to the Applications of Derivatives unit. This unit has a lot of vocabulary and conceptual thinking, so get ready to think conceptually. Let's start by defining these words. Increasing means that the slope is positive, it's going up. Decreasing means that the slope is negative, it's going down. Concavity looks at the rate of change of the slopes. In this graph, the slope starts negative, but then it becomes zero, and then it becomes positive. The slopes are increasing, we call this concave up. Just like that, the slopes here are decreasing, we call it concave down. I remember it as concave up being a smiley face and concave down being a sad face. Another way to think about it is that if your tangent line is above the graph, then you have concave down. If your tangent line is below the graph, then you have concave up. Now, whatever method works for you, go ahead. Anyways, but just notice that if the graph is increasing or decreasing, the first derivative is positive or negative respectively, just by looking at the slope. And also notice that when the graph is concave up, its second derivative is positive because the slopes are getting positiver. When it's concave down, the second derivative is negative because the slopes are getting negativer. Keep those facts in mind because we're going to define some tests using those facts in a few minutes. An example problem for this might be to draw a graph given information about a function and its first and second derivatives. Now let's talk about extrema. First, a bunch of definitions. A critical point is where something interesting is going on. There might be a tangent line or there might be a sharp point. A stationary point is where the graph has a derivative of 0. It has a horizontal tangent line. A relative minimum is the bottom, where there's a horizontal tangent line and the graph switches from decreasing to increasing. A relative maximum is the opposite. It switches from increasing to decreasing. These relative maximum and minimum are collectively called relative extrema. If you're given a section of a graph, the endpoints cannot be relative extrema because you don't know what's going on the other side. An inflection point is where the concavity switches. It is where the tangent line switches from over the graph to under the graph or vice versa. By knowing the signs of the first and second derivative, you can learn a lot about a graph. Look at this table. It has a lot of information about what you could learn. To find a relative extrema, you can use the first derivative test. First, take the derivative, then find where it is either 0 or it is undefined. These are your critical values. Put these values on a number line, then plug numbers between the critical numbers and on either ends into the derivative. Write the sign of your answer in the appropriate place, plus or minus. So for example, say this is plus, this is minus, and this is plus. If there's a switch from positive to negative, this point is a relative maximum. If it switches from negative to positive, this point is a relative minimum. If the sign is the same on both sides, then there is no relative extrema at that point. You can also find relative extrema using the second derivative in the second derivative test. Again, a very creative name. So you first need to find critical points using the first derivative, but then you simply plug those points into the second derivative. If the output is positive, then it's a relative minimum. If the output is negative, it's a relative maximum. If the output is 0, then there's no conclusion. You then have to use the first derivative test. You can also perform the first derivative test for the second derivative. Find the critical points, put it on a number line, and check the signs. If the sign is positive, then the graph is concave up in this section. If the graph is negative, then it's concave down on this section. These critical points, where the sign switches, are the inflection points. Okay, now let's move on to absolute extrema. Thankfully, these are a bit simpler. The absolute maximum is simply the highest point on the graph, and the absolute minimum is the lowest. There's a pretty straightforward theorem called the extreme value theorem that says that all continuous graphs across a finite interval have an absolute maximum and minimum. Here's how to find them. To find absolute extrema across a closed interval a to b, first find the critical values by the methods we did before. Make sure the critical values are in between your endpoints. Then you plug those critical numbers back into f of x. In addition, plug both endpoints into f of x as well. Then we have a table here with the inputs in the x column and the outputs in the f of x column. The biggest output is the absolute maximum, and the smallest output is the absolute minimum. By the way, here's one small thing that people often mess up. When a question asks you for where the absolute extrema occurs, you list x values. If it asks you for what the extrema are, you list y values. Now let's talk about optimization. These are problems where you want to find the highest or lowest some value can be, given some restrictions. Let's go through the steps with this problem. The first step is to figure out what we know, what they're asking for, and whether we want to minimize it or maximize it. So, Farmer Bob and Farmer Susie have asked you to build a fence for their farm because they're farmers who have a farm. They give you 100 feet of fencing, and they ask you to maximize the enclosed area. What is that area? Okay, so we know the total perimeter has to be 100, and we want to maximize the area. The second step, let's draw a picture. So we're going to have a farm, a rectangular fence there. Let's call this side x and this side y. Now, let's write some equations. We have two variables, so we want two equations. The area is xy, so we want to maximize xy. We also know that the perimeter, which is 2x plus 2y, equals 100. So y equals 50 minus x. The next step is to rewrite the equation that we want to maximize in terms of one variable. So I'll just take this and plug it into here. So that'll give me, we want to maximize x times 50 minus x. Ignore the random spikes, that's just some weird glitch. So let's do this. We want to take the derivative of this. We'll get, well, let me actually expand it first. We'll get 50x minus x squared. So if we take the derivative of this, we'll get 50 minus 2x. And if we set this to 0, so I'll say 50, oh my goodness, 50 minus 2x equals 0. Oh, I'm going on the bottom. I'll do over here, x equals 25, right? So the maximum x value is 25. Since 2x plus 2y equals 100, I know that means y equals 25. The maximum area is x times y, which is 25 times 25, which is 625 feet, square feet. So we just use calculus to determine the maximum fenced area. Now, let's talk about the mean value theorem. If we have a graph from, let's say, A, some random point, to, I don't know, B, that is continuous and differentiable, meaning there are no sharp points, then the average slope from A to B will be equal to the derivative of f of x at a point C, which is in between A and B. So I'll re-explain that in English. What that means is, if we take the average slope between the 2 points A and B, which is just a fancy way of saying connect the dots, then this tangent line, or so this average slope, will be equal to the tangent line at some point. In this graph, that looks to be around here. It's the same slope. Rolle's theorem is just a special case of the mean value theorem. It says that if the function is continuous and differentiable on a to b, and that f of a equals f of b, so let's say here's our a, and here's our b. Notice that in this case, f of a and f of b are both 0, then there is one value c in between a and b, where f prime of c equals 0, or there's a horizontal tangent. Basically, in between these 2 points, since they have the same y value, there's some point in between them where there's a horizontal tangent. In this case, that's right here. Again, realize this is just a special case of the mean value theorem where the average slope is 0. Okay, I'm going to flip to the next slide. Don't get overwhelmed. Hold on. Okay, so let's go through this slowly. The last topic in this unit is rectilinear motion. This is the straight line motion of an object or particle. There's a bit of vocabulary for this section as well. Position is how far it is from a certain 0 point. Velocity is the time derivative of position, and acceleration is the time derivative of velocity. When the velocity is positive, that means the object is moving in the positive direction. When it is negative, the object is moving in the negative direction. When it is 0, the object is not moving at all. When the acceleration is positive, the velocity is becoming more positive. And when it's negative, the velocity is becoming more negative. A positive acceleration does not mean it is speeding up. If the particle has a negative velocity, and a positive acceleration would make the velocity less negative, so it would become closer to 0, so it would be slowing down. For a particle to be speeding up, the velocity and acceleration must both be in the same direction, either both positive or both negative. If they have different signs, then it's slowing down. On the diagrams to the right, the blue arrow is the velocity, and it shows what direction the object is moving in. The red arrow shows the acceleration. So I know this slide is a lot. Take a second to pause and take it all in. We'll get to these bottom two on the next slide. Another nuance to be aware of is the difference between distance and displacement. So displacement is just the final distance minus the initial distance, the net change in position. Distance, on the other hand, is how much you moved in total. If I walk 2 feet forward and 2 feet back, my displacement is 0, but my distance is 4 feet. If a problem asks you for distance, you need to find the critical points and add up each of the displacements. For example, in my previous example of walking, there was a critical point after I walked 2 feet because I had to stop, turn around, and walk backwards. So in this case, you'd find the first displacement, which is 2 feet, then you'd find the second displacement, which is also 2 feet, and you'd add those together to get your final answer of 4 feet. So there's a good chance that you didn't completely understand everything I just said in this video, which is totally fine. I'm going super duper fast. I'd recommend that you rewatch the parts that you're having the most trouble with, and then I'd also recommend that you watch videos on Khan Academy or another place where they go into a lot more detail. Also, the problem solving video where I solve relevant problems in this unit might also help clarify some things. Anyways, that's all for this unit. Goodbye, and I'll see you next time.